This problem asks us to consider the continuity of a given function. So before worrying about the function, let's review what we mean by continuity. Loosely speaking, a function is continuous if we can draw its graph without picking up our pen or pencil. But we want to be a little bit more mathematical than that here. Recall that we developed a number of conditions for a function to be continuous. And so our function is continuous at some given x value if the first requirement is that the function is defined at that x value. Certainly if we're going to draw a graph through some point, there's got to be a point there to start with. So we require that the function have some value when x is a. Second, we require that the two-sided limit as x approaches a exists. And this condition prohibits any jumps or breaks or vertical asymptotes in our graph. And third, we require that the limit as x approaches a of our function is the same as the function value. And this condition prohibits any holes in our graph. Right? So for a function to be continuous at some x value, all three of these conditions must be met. So now that we've reviewed that idea, let's go ahead and take a look at this particular function. This is a piecewise function. If x is less than or equal to 1, then we use x squared to find our function value. And if x is larger than 1, then our function value is always -1. So since we're talking about continuity, it's a good idea to have a picture. So let's go ahead and sketch the graph of this function. In the left piece for x less than or equal to 1, I'm just going to draw the graph of x squared, which will look something like that. And it's going to stop at the point 1, 1. And notice that I've used a solid dot at the end of this piece because of the less than or equal to sign. For x greater than 1, we just want to draw the constant function f of x equal to -1, so that's just a horizontal line starting at 1, -1 and heading out to the right. And here we use an open hole because of the strict inequality. Right? So just looking at the graph, we know that when x is equal to 1, there is a jump. So our function is discontinuous at x equal to 1. But everywhere else we can draw it without picking up our pen, so it's going to be continuous at any other x value. Right? But to answer this question, we want to use those three conditions that we came up with. So we notice that the limit as x approaches 1 from the left is equal to 1, and the limit as x approaches 1 from the right along this piece is going to be equal to -1. Now because the limits are different depending on how x approaches 1, we know that the limit, the two-sided limit, as x approaches 1 of our function does not exist. And this was the second condition for continuity. So because of this fact, we conclude that f is discontinuous